Welcome to some free GCSE tutoring. You asked me guys some questions in a community post and I'm going to be going over all of them. Keep in mind that you can learn a lot from what other people have asked. So the first question that you guys asked me was about lens diagrams and if I could go over them. There are two types of lenses that we need to know about. We have convex lenses, which are also known as converging lenses. So they're actually the same. We also have concave that I'm going to be talking about in a minute. So the convex, or also known as a converging lens, actually looks a little bit like this. So it is bulging out. Let's say that we want to draw a ray diagram. So let's say that we have an object, maybe something as simple as an arrow. The light rays of that arrow or whatever the object is are going to go through the lens and then they're going to get refracted through the focal point. See if I can draw this a little bit better. It's a little bit hard this with a digital ruler, but they're going to go through here and then this one here, so the ray from the bottom is going to go through this one like so. First of all, the ray that is from the bottom has gone through here, it's changed direction, gone through the focal point and it's reached up here. And the ray from the top has gone down here, meaning that our image will actually be inverted. So the top bit of the arrow has gone down. Additionally, notice that this image is now bigger. So we can, how do we classify this image? Well, first of all, we can say that it's inverted. It is also magnified or increased in size or similar word. And it's a real image. How do we know that it's a real image? It's to the right of the focal point. We follow the rays and we look through this and we immediately see the image. Now these are to be contrasted with a concave lens, and depending on the example you may also come across the word diverging lens. So what do they look like? Well, they're concave as the name suggests. One light ray from an object, in this case this arrow, is going to go through here, and then another one, the one that goes through the focal point, is just going to go straight in undisturbed. But notice that those two rays are going far apart from one another, i.e. they are diverging. So those will actually create a virtual image. How do I create a virtual image? I imagine where this ray is kind of continuing, so I'm going to draw a dotted line, and where it meets the other ray, it is going to form an image. The image, so just draw that in a different color, I'm going to draw that in green, is going to look like this and is going to have the following properties. So number one, notice that it is smaller than the original image, and we call this that the image is diminished. It has a lower magnification, or it's smaller. We will also say that this here is a virtual image because it's on the same side compared to the focal point. It's on the same side as the object. And notice that this image is not inverted either. Next question, can you go over 6-mark magnetism questions like why coil rotated continuously, etc.? Okay, well, let's draw a coil between a magnet. Well, here's my drawing across here. We have a magnet and the field lines are going to be going north to south. And here I've got a wire that essentially is spinning between the magnet. So in a way, this here is an electric generator. There will actually going to be a current that's produced. Well, why is that? Let's put that into a typical sort of extended response question form. Well, here are some of the typical marking points in kind of a 6-marker form. First of all, when the coil moves, that's actually kind of an important one to to add in that the coil is moving in the magnetic field. And as it's moving through the magnetic field, it cuts through magnetic field lines. Also, as a reminder, magnetic field lines always go from north to south, just in case you're being asked to draw them on a question. So let's just draw a couple, it doesn't hurt drawing a few. Or maybe asked to state their direction, etc. So because the field is uniform, they should be more or less equally spaced. There we go, we've drawn 3 of those lines. They're going north to south. We could also use Fleming's left-hand rule if you wanted to determine the direction of the current. That's a whole different story. Okay, now back to the 6 marker. It will cut through the magnetic field lines. Now, every time you have a moving wire in a magnetic field, what you're going to get is that a PD is induced across the coil due to something known as Faraday's law. Now, if a PD is induced, then also a current will be induced. And something really important, every half a turn, the current will change direction as the coil is changing direction. And every half a turn, the PD will also be changing direction. In practice, this leads to the classic AC graph of sort of current against time. It kind of goes positive to negative, like so. Okay, next question. Can you go over the iGCSE 2023 syllabus, space physics topics such as the Doppler effect, Hubble's constant, stars, and the life cycle CMBR? Okay, so this is a very, very vast topic, and there's quite a few things that not all exam boards need to know. So if you're not doing iGCSE, just check with your syllabus before trying to learn what I'm going to say. Okay, so shall we start off with the Doppler effect? You guys don't actually need to know the equation of the Doppler effect, but it is a method of determining the speed of distant galaxies. So using the Doppler effect, we can determine the speed, let's call that V of distant galaxies. The Doppler effect actually tells us that wavelengths are stretched if things are moving away from us. Imagine you're holding a slinky and creating a wave and then running back. Actually, don't do that, that's dangerous. And then the wave will get stretched. On the other hand, if you are kind of going in the other direction and the wave is also going the other direction, then it may get compressed. And that's, in a nutshell, the Doppler effect. It allows us, by looking at how much the waves have stretched, we can determine their speed V and the direction of that speed. Once we apply this to all the different galaxies, we come up with a very, very interesting equation that links them. A typical graph for this involves the speed of the galaxies against distance from the Earth, and it turns out that there's pretty much a straight line correlation between them, meaning that they are directly proportional. And this here is Hubble's law, that the speed, this should really be going for the origin, but the speed of a distant galaxy is proportional to its distance from Earth. If something is proportional, there should be a constant, and that constant is known as Hubble's constant. So this here, V, is known as the recession speed. H naught is Hubble's constant. And D is the distance to the galaxy. We can really just rearrange this for Hubble's constant and define it in terms of this equation. So Hubble's constant is just a ratio of the speed of recession of the galaxy, or the speed of the galaxy, divided by its distance from the Earth. Our current measurements give us a value of H0 that you need to remember for the exam if you're doing iGCSE. I don't believe that's the case for the other exam boards, but it's around 2.2 times 10 to the power of minus 18, and the unit of it is seconds to the power of -1. So it has inverse units of time. So that's 1/seconds. The exam board often calls that just, I'm just going to write it in brackets here, per second. So 2.28 times 10 to the power of -18 per second. Now, because it's 1/second, we can actually flip both sides of the equation. So we can do 1/h0, and this will mean if we flip the left-hand side, we also have to flip the right-hand side. So this will give us d/v, and this is actually an estimate for the age of the universe. If you're interested in more about that, check out my cosmology video on my A-level physics channel, Z Physics, in which I go into this in a lot more depth. Now, you also wanted to know about the CMBR, so I'm going to go for the CMBR before I go through stars. Well, the CMBR is a microwave radiation that is measured at every point in space, and this actually is a remnant of the Big Bang. So it started off as gamma rays that have now been stretched to microwaves, and that is one of the biggest pieces of evidence for the Big Bang. Okay, just one more thing, and that here is stars, isn't it, and their life cycles. Now, I have a whole separate video for that in which I go over this in quite a lot of detail, and it's about space physics minus the Hubble law stuff, but I'm going to link that in the description of the video. So for stars and life cycles, have a look at that. Okay, next one, which is the radioactivity question from the 2019 Combined Science trilogy. So that's question 6. So this is a really fun radioactivity question. We have the number of particles on the y-axis, and notice that the numbers are multiplied by 10 to the power of 23, and we have the time in seconds. And we're being asked to find the activity at a time when t is equal to 20 seconds. Well, what is the activity? Remember, it's defined as the change of particles, how many particles have essentially left the radioactive substance, divided by time. So because of that, the activity will essentially be the gradient if this was a straight line graph, but it's not quite a straight line graph. Notice that there's a curve, so it will just be the gradient of the tangent. So let's draw a little tangent. So what I'm going to do is essentially just find a line that follows the general trend. So we'll just do that in a different color. So let's say that here is our tangent. And if you do that on the question paper, which I've done, not on my digital whiteboard, I got a couple of numbers here. So it crossed the axis at around 4.8, well, times 10 to the power of 23, don't forget that, and crossed the x-axis at around 86. And there's a range that's given in the mark scheme, so as long as your values are somewhere close to those, it will be fine. And because of that, we can find the gradient. In other words, our delta n will be 4.8 times 10 to the power of 23, at least for my gradient. Divide that by 86. And if we were to calculate that with a calculator, I'm going to get around 5.58, let's call it 5.6 times 10 to the power of 21. And there's quite a generous range in the mark scheme, anywhere between, I think it was around 4.9 times 10 to the power of 21, up until around 5.9 times 10 to the power of 21 will give you full marks. And remember, the units for that are becquerels for the activity. Okay, next question. Can you go over the OCR J250 syllabus and cover half-life and particle decay? The answer to this is that I have done this already, and you check out this video right over here that I'm going to leave with a card, and I'll also link in the description. Do let me know if you have any questions or if you'd like me to cover something else that's not been covered in the video, but I think I've pretty much covered it all right here, so I hope that's useful. Okay, next one, we have an ice cube which has a temperature of minus 15 degrees Celsius. The total thermal energy needed to raise the temperature of this ice cube to 0 degrees and completely melt it is this many joules, and we're given the specific heat capacity of ice and the specific latent heat. Calculate the mass of the ice cube, and it's going to be quite a long calculation. The trick with these questions is to always think of the total energy. I'm going to say that the total energy, E total, is going to be a sum of two things. Let's say that we have E1 plus E2. Now, E1 will be the energy required to raise the temperature. So raise the temperature to 0 degrees. And this will be using the specific heat capacity. After we're at 0 degrees, all of our energy will go into melting. So this here will use E is equal to mc delta theta, and this one here will just use our specific latent heat equation, which is that E is equal to m times the specific latent heat of fusion. Okay, well, our total energy, which is 5848, will be equal to m multiplied by C, which is the specific heat capacity of ice, which is 2100, times the change of temperature. If we're going from minus 15 to 0, then our change of temperature will be just 15 degrees, and to that we're going to add m times L, which is the specific latent heat, which is just, I'm going to add in some brackets, 33400, like so. Okay, well, we've got all the numbers, and what we can do is we can take a factor of m outside of these brackets. So I'm going to get 5848, and then just like in maths, I'm going to factor out m, and what I'm left with is 2100 times 15 plus 334,000. So I've just taken m outside of the brackets. Now I can just rearrange for m, and the mass will just be equal to 5848 divided by that number. This could be x, it could be anything, whatever you want to call it, but it's just 2100 times 15 plus 334,000. And quick unit check, they all seem fine. I can just plug that into a calculator, and we are going to get 0.016 kilogram. If you need that in grams, this is equal to 16 grams. Okay guys, well, I hope this was useful. I think I've covered all the questions that you've asked me. If there's something else, do let me know, and hopefully this helps your revision. If you're curious how to revise and to have a look at some interesting techniques on revision, have a look at this video right over here.